Another fun thing to do with the fundamental theorem of calculus is to take, let's say, an area accumulation function, so the g of x, and we'll say g of x is the integral from 0 to x of f of t dt. Notice that these are t's because x is already being used. And because this is calculus, we're going to take the derivative with respect to x of both sides, because we can do that because it's calculus. Alright, on the right side I just have the derivative of g of x, and on the left side I have the derivative of, wait for it, the integral of 0 to x of ft dt. Let's think about this for a second. I'm taking the derivative of an integral, or antiderivative. So like the derivative of an antiderivative. Pretty sure that there should be some like canceling out going on, because derivative and antiderivative sound like they're opposites. Well, guess what? They are. So this problem is actually really easy. G prime, which is the derivative of g of x, is just going to be equal to, here's what we do. Watch it. It's going to be fun. We take f, whatever the function is, and we take the variable, and yeah, we just plug it in for t. Yeah, that's it. So guess what? G prime of x is equal to f of x. Ta-da! Oh, except it's not. Remember, this is a derivative, so we have to do that nasty thing called the chain rule. And so a 1 comes out, but yeah, cool. Let's look at an example at this to kind of see how this comes together. So let's say I have g of x, and g of x is the integral from, let's not make it 0, let's make it like 3 to x, and we'll have t squared minus 2 dt is my function. And I'm going to find g prime of x, and I'm going to do it the old-fashioned way. So what I'm going to do is I'm going to find the integral first, and then take the derivative of it. For most of these problems, you won't do this because you probably can't find the integral, and that's okay. I'm just going to show you that this does in fact work. So I take the integral. Well, the integral is of t squared. Let's see, add 1, divide by the new power. That's a plus. I'm going to get t cubed over 3. Then I'm going to get minus 2, the integral of minus 2 is minus 2t, okay? And then plus c, I don't really need the plus c because this is a definite integral. And then remember that I'm evaluating this integral from 3 to x. So I do this just like I do normal antiderivatives. I have that because that's still on the outside there. So I plug in x for t. And so I get x cubed over 3 minus 2x, parentheses, minus 3 cubed over 3 minus 6. Okay, I just plugged 3 in, subtracted. This is my fundamental theorem of calculus. Cool. Oh, I'm not done yet because now I'm going to take the derivative. So the derivative, I just take the derivative of everything. This is an x, ddx. I messed up, ddx. The derivative of x cubed over 3 is just, well, it's 3x squared over 3, which is just x squared. Very nice. And the derivative of negative 2x is just negative 2. And those are all constants. So plus 0, or just go away, yeah. So I get x squared minus 2, which should seem very familiar because guess what? It's what we started with. Except, guess what? Remember, instead of t's, you put an x in there. So instead of t squared minus 2, it's x squared minus 2. And there's no chain rule because we started with x. That's it. Done. Easy. Mr. DRM, you can't be serious. Really? They're that easy? Yes, they are, in fact. Let's say I have g of x equals the integral from negative 4 to x of, let's see, x, no, not x, because I can't use x, t squared times the sine of 7t dt. Ha! You don't know how to do this integral, and you probably won't learn it until chapter 8, if you're even doing chapter 8. Anyway, whatever. But guess what? So I can't find what g of x is. Let's just leave it at that. But I can find g prime of x. It's very easy, because all I do is take this function and plug in x. So it's going to be x squared times sine of 7x. And my chain rule, okay, be very careful. The stuff is x, okay? So if this is just an x up here, my chain rule is just a 1. That's it. No product rule, no 7s coming out, just x. Or just 1, rather. So that's it. That's G prime. It's really that easy. Mr. DRM, you keep going on about this whole chain rule thing with this fundamental theorem, and I don't get it. Well, here's how to deal with a chain rule example. Let's say we have the integral from negative 2 to x of sine of t squared dt. Oh, and instead of x, we'll make it x cubed, just to be fun. Well, I'm going to treat this the exact same way. So I'm asked to find g prime of x. Find g prime of x. Well, I'm doing the derivative of an integral, d dx, and so essentially they cancel. I plug in x cubed in for t. And so watch. I get sine of stuff squared. And the stuff is x cubed, because that's what's up here. And then I chain rule 3x squared. I only chain rule the variable part of the limit of integration. I don't chain rule the squared. I don't chain rule sine. I only chain rule the x cubed. And that is my answer. That is the derivative of this particular integral. And the last one, just for fun, to make you think a little bit, let's say I have g of x equals the integral, from negative 2 to 4 of, I don't know, we'll do like cosine of t, cosine of t times, why not, t squared, and actually this is not just negative 2, it's negative 2x. I guess I missed that. Alright, so here's my integral. Negative 2x to 4 of cosine of t times t squared dt. Again, we don't know how to integrate this, but I do know how to find g prime of x. Oh, well, here's the issue with this one. With this one, the variable is the bottom limit of integration. And this is slightly different. In order to do this problem, there's two ways to think about it. The first way is to just flip the limits. Put the negative 2x on top and the 4 on the bottom. Remember, if I flip the limits, I have to make this negative, because it means now I'm integrating backwards from what I was originally. And so this would be cosine of t, t squared, dt. So I have the negative here, negative. I take cosine, and instead of t, I have negative 2x. And instead of t squared, I have negative 2x squared. And I have negative 2x. It's stuff. I chain rule the negative 2 out, and that is my final answer. So negative, cosine, stuff, stuff squared, chain rule, just the stuff. I did mention there was a second way to think about this, and the second way to think about this is that with your fundamental theorem, essentially when you take the derivative, you'll have blah 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 minus blah blah blah. And the first blah 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 will have the x equals 4 plugged in. No, t equals 4. When you're evaluating that FTC, the first blah 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 will have the t equals 4. The second blah 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 will have the t equals negative 2x. So when you do this, and then when you take that derivative, ddx, this is going to be the constant stuff. And this negative will stay there. And so these two negatives are in fact the same. Then you're just going to plug that negative 2x in for t and get that. So there are two ways to think about it if the limits are flip-flopped, basically.